So we just finished Laplace transform and inverse Laplace transform of some unit step functions, shifted unit step functions and window functions. Now I'm going to move on to another type of function. It's called periodic functions. So what is periodic functions? So a function f of t is said to be periodic of period t. Capital T has to be different from 0 if the function f of t can be written as f of t equal to f of t plus capital T, or f of t equal to f of t minus capital T, for all value of little t in the domain of f. Okay, so graphically, the periodic function has repetitive behavior. So let's take a look at this particular function. So the graph of this function has repetitive behavior. You have the function of the form f of t equal to 1 when t is between 0 and 1, and equal to -1 when t is between 1 and 2. And if you use this particular function and copy that to the next interval between 2 and 4, you have the same behavior. Or you take a look at, or if you take this function and copy it back to the interval between -4 and to the interval between -2 and 0, you have the same behavior. So this is called periodic functions. More specifically for this functions that we're looking at, this is called the square wave function. So the functions is written in terms of piecewise defined functions. This function is periodic and with period 2. So the functions is periodic with period 2. Now, sometimes it is convenient to introduce a notation for the window versions of the periodic functions f of t. So let's take a look at this particular graph. So the entire blue curve is f of t, which is the periodic functions. Now, if we just take a look at part of the periodic functions, like apply a window function into f of t, we have the function f sub capital T of t. All right, so that is the window function for the periodic functions. Okay, so this is the window versions of a periodic function f of t using a rectangular window. Whose width is the period. All right, so how can you get the window versions of periodic functions? So the window versions is f sub t of t, and is equal to the periodic functions times u sub 0 comma capital T of t. So we just want to look at the window versions of the periodic functions, and the window function has the width from 0 to capital T. So that's why you apply this window functions of the form u sub 0 comma T of t. So the idea of the window versions of periodic function is that you can just look at the functions as at a certain window with certain width, and do analysis on that window versions, right? And because periodic function, it has repetitive behavior, so whatever you know about window functions, you can just copy the information and paste that to other parts of the periodic functions. So it's quite helpful that way. All right, so f sub capital T of t is defined to be f of t times u sub 0 comma T of t. This is the window function u sub 0 comma T of t. It can be written as the unit step function and the shifted unit step function as follow. So this is equal to f of t times u of t minus u of t minus capital T. And then you rewrite u of t and u of t minus capital T in terms of piecewise defined functions as follow. You have little f of t times the piecewise defined functions of u of t. This is equal to 0 when t is less than 0, and equal to 1 when t is greater than 0. Minus the piecewise defined function of u of t minus capital T. That is, the function is equal to 0 when t is less than the period, and equal to 1 when t is greater than period. All right, so we have done something like this earlier in the lecture. What you do is that you look at the interval on the real line here, this is 0, this is capital T. Then you have 3 different intervals that you need to consider. The interval when t is less than 0, the interval when t is between 0 and the period, and the interval when t is greater than the period. Okay, so the first interval that we need to consider is the interval when t is less than 0. Right, so 0 here. Simultaneously, in the second function, you have 0 when t is less than the period, because when t is less than the period, the entire function, the red line, is equal to 0. Not only that, the function is 0 when t is less than the period, is also 0 when t is less than 0. So 0 here when t is less than 0, and equal to, now go back to the first functions and consider the second interval from 0 to capital T, and the function is equal to 1 when t is between 0 and capital T. But for the case of the second function, you have the function still to be 0 when t is between 0 and the period. And for the last part of the first function, the function is equal to 0 when t is greater than capital T. And here, 1 when t is greater than capital T. Now you can combine these two piecewise defined functions together to get f of t times the piecewise defined function of the form. So 0 minus 0 becomes 0 when t is less than 0. 1 minus 0 is equal to 1 when t is between 0 and capital T, and 1 minus 1 is equal to 0 when t is greater than capital T. And then you can multiply the f of t into the piecewise defined functions, and you get this is 0 when t is less than 0 is equal to f of t when t is between 0 and the period, and is equal to 0 when t is greater than the period. Alright, so that is the window versions of the periodic functions. Now you can present the function in terms of piecewise defined function like this, or you can shorten it a little bit as follows. So the function is equal to little f of t when t is between 0 and the period, and 0 otherwise. Okay, so again, that is the window versions of the periodic functions, given that the period is equal to capital T. Now, most often you want to find the Laplace transform of the periodic functions, and I'm going to give you the formula to find the Laplace transform of the periodic functions and how they connect between the Laplace transform of the periodic functions and the Laplace transform of the window versions of the periodic functions. So that is the next theorem, so transform of periodic functions. So if little f has period t and is piecewise continuous on the interval between 0 and t, then Laplace transform of the functions, so capital F of s, equal to the integral from 0 to positive infinity of e to the negative st times f of t dt. Again, this is the definitions of Laplace transform of a functions, given that the functions f of t is a periodic function in this case. Now, the Laplace transform of the window versions of the periodic functions has the form capital F sub t of s equal to the definite integral from 0 to t. So this is no longer the improper integral. We just look at a part of the periodic function. So therefore, the improper integral becomes the definite integral from 0 to t in this case. So the integral is of the function e to the negative st times f of t dt. And these two Laplace transform are related by the formula, that is capital F sub t of s equal to capital S times 1 minus e to the negative st. Or you can solve for capital F of s as follow. So capital F of s equal to capital F sub t of s divided by 1 minus e to the negative st. Okay, so I just divided both sides for this term. So that's the formula. Where is this actually coming from? So I'm going to show you a quick proof on this. It's very straightforward. The assumption is that the functions that you're working with is the periodic functions with periods capital T. All right. So as before, I'm going to start out with the window versions of the periodic functions. I write that in terms of the periodic functions and the window functions, and I got this information right here. So f sub t of t is equal to f of t times u sub 0 comma t of t, or this is equal to f of t times u of t minus u of t minus capital T. Then distribute f of t into the bracket. You have f of t times u of t minus f of t times u of t minus capital T. Now, eventually, you have to take Laplace transform on both sides of the equations, and you look at the formula that we need for the Laplace transform in the Laplace transform table. And with your experience with the examples that we did earlier, you want to change this part of the equations to f of t minus capital T times u of t minus capital T, so that you can use the Laplace transform a little bit easier. So how could you go from f of t to f of t minus capital T? Remember, you are working with periodic functions, so little f is periodic functions, and by the definitions of periodic functions, f of t is equal to f of minus capital T. So you can rewrite this as f of t times u of t minus f of t minus capital T times u of t minus capital T. Then you apply the Laplace transform on both sides of the equations. So this is little f sub t of t. When you apply the Laplace transform on both sides of the equations, the left-hand side becomes capital F sub t of s equal to Laplace transform of f of t times u of t minus the Laplace transform of f of t minus capital T times u of t minus capital T. All right. Now you go back to the Laplace transform table and look up the two formula that you need for this calculation. So for the Laplace transform of f of t times u of t, you can use this particular formula as well, with the shift to be c equal to 0, so that means there's no shift at all. So c is equal to 0 implies that e to the 0 is equal to 1. You just get the Laplace transform of the functions f of t, right? So it's just capital F of s. Now for the Laplace transform of f of t minus c times u of t minus c, then is equal to e to the negative cs times capital F of s. But remember here the shift is equal to the period capital T. So let me go back to the note here. So capital F sub t of s is equal to, here you have capital F of s minus e to the negative st times capital F of s. Now, if you take capital F of s as a common factor, you're left with 1 minus e to the negative st, and you get the formula right here. Okay, so that's the Laplace transform for the periodic functions and for the window versions of the periodic functions. Now let's take a look at the following example. This is again the square waved functions, and you want to find the Laplace transform of this periodic functions of the window functions. So this is the window part of the periodic functions. So the entire function is little f of t periodic functions, f of t with period capital T equal to 2. So let's rewrite this window versions of the periodic functions a little bit. So we did something like this earlier in the notes already. So little f sub t of t is starting at 1. So you have 1 times u of t, and then you go from 1 down to negative 1. So you go 1, 2 units, or you just let new functions minus the old function, that is negative 1 minus 1, you get negative 2, and this is use of t minus 1. So you have the unit step function and the shifted unit step functions. All right, then you apply the Laplace transform on both sides of this equation, see what you get. That is Laplace transform of f sub capital T of t equal to Laplace transform of u of t minus 2 times the Laplace transform of u of t minus 1. So Laplace transform of u of t is equal to 1 minus 2 times Laplace transform of u of t minus 1 is equal to e to the negative s divided by s. Right, again, I just go to the Laplace transform table and look for the Laplace transform of u of t minus 1. And the left-hand side is the capital f sub t of s. Right, so that is the Laplace transform of the window function. Now, to find the Laplace transform of the periodic functions, you get capital F of s equal to capital F sub t of s divided by 1 minus e to the negative st. For capital T is equal to 2 in this case, so you have 1 over 1 minus e to the negative 2s times the Laplace transform of the window versions of the periodic function, which is 1 minus 2 times e to the negative s divided by s. And that is the Laplace transform of the periodic functions that you're looking for.